I don't have my mic on. That's a problem. Uh, my bad. Hopefully everyone can hear now. I just was saying that we're going to be studying kinetics today, which is chapter 14 in our book. We're dealing with basically how fast reactions go, like what are their rates. And we're going to see that this is actually a way we can talk about how reactions are happening, but that's going to be a little bit later on. So for right now, it's just we're looking at speeds of reaction. How are things changing over time? However, if any of you have any questions on solutions, I'd be happy to go over some of those now, if any of you like, or we can just jump right into kinetics. So happy to do either one. So I'm gonna guess I'll start with kinetics. If any solution things come up, throw them out there. We'll see what we can do. Alrighty. We're gonna see that later on. We're gonna be able to kind of not necessarily transform, but kind of infer from the rate of a reaction. We're going to be able to determine the mechanism of reaction. And this is actually quite important because if you know how reactions are working, that's what the mechanism answers. It answers how something is happening. It'll give you kind of information that you can use in very important applications, like pharmaceuticals, for example. If you understand how an enzyme is working, if it's doing its job catalyzing some reaction, the more you know about that particular mechanism, the more insight you'll have into how to design a drug that will affect that enzyme in a particular way. So if any of you are thinking about pharmacy or pharmacology, you'll be dealing with kinetics quite a bit, especially if you go into biochemistry. You'll have entire classes just on enzyme kinetics. It's quite a important topic there. But also, if you're a pure chemist like myself, studying mechanisms of reaction is very important, and kinetics is a big part about kind of elucidating how reactions are happening. So that's kind of the whole goal of this learning about all this kinetic stuff, is to understand how we can kind of get information about mechanisms of reactions. All right, but for us, we can just start at the beginning here with kind of kinetics. Basically, the rate of a reaction, whatever it may be, we're going to see that that's going to be the change in concentration over the change in time. That's going to be kinetics at its most simple form. Let's write that in words. Over time. So we're looking at, we can either be looking at the rate at which a reactant is being used up, or the rate at which a product is being produced. So how these things are changing over time. Of course, as a product is being produced, that's going to be increasing its concentration over time. If something is being consumed, it'll decrease its concentration over time. And so while technically rate can be either positive or negative, let's write this in purple because why not? This can be positive or negative. We always use the positive one because we're talking about rates. No one talks about negative speed. I mean, you can have negative velocity if you're going away from, the point of interest. But we're just going to, by convention, just have everything be positive because that's what we like to do. So let's look at first, we're going to look at things that kind of can affect the rate of a reaction. And we're going to talk about all of those through this kind of chapter. we're going to have a number of things here. Perhaps the one that is most, I don't want to say important, but the easiest one to manipulate for us is the temperature. The hotter things are, the more they're moving. We know that temperature is related to kinetic energy. The faster things are moving, the more energy they have, the more likely they are to react together. We'll go over that in just a second. But suffice it to say that an increase of roughly 10 Celsius is approximately equal to doubling your reaction rate. So if you increase something by 10 degrees Celsius, you are going to be doubling its reaction rate. If you increase it by 20 degrees, you're going to be quadrupling its reaction rate. Or if you cool it by 10 degrees, you're halving its reaction rate. This is, it's not exactly, 10 and 2, but it's pretty close to that. So, just kind of keep that in mind. A rough estimate of how temperature affects reaction rates. And we're going to see that this is primarily because faster molecules mean more collisions. And importantly, more collisions with high energy. So if we go ahead and look back at our absolutely favorite Boltzmann distribution, we have our proportion, we have our kinetic energy. Remember, here's a particular temperature, and if we increase the temperature, now we will have like a graph like that or something. Remember that we'll say that this is some higher temperature, whatever that may be. The purple one's the higher one. Of course, you don't have negative proportion, but that's okay. You can see again in our graph here that you're going to have a higher proportion of molecules with higher energy at a higher temperature. And so we're going to see that that's going to affect your rate of reaction by allowing molecules to collide, one, more frequently overall, and two, more likely to have enough energy to undergo a reaction. We're going to see that when we look at kind of an overview of how reactions happen. All right, and so, yeah, temperature. Cool. Another one we have is concentration. So we're going to see that reactions are all about collisions. And so the higher concentration we have, that just means they're more likely to collide, right? And so, the more there are in there, the more likely they are to hit each other. Just kind of basic probability, right? The more likely, potential events that could happen, the more likely one of them is to happen. So we're going to see that all this stuff actually kind of relates to the gas laws. We saw that increasing temperature increased pressure. We are going to see that increasing the moles also increases the pressure, right? It's the same as the gas law sort of thing. And now for the volume aspect. We're going to see that the state of matter is also going to be an important thing here. We're going to see that liquids and gases and solutions in those phases react much faster than solids. In fact, some could say that solids, if you just have two solids put together and you're trying to get them to react, probably not going to happen because solids just don't move. They vibrate in place, but they're not really moving. And so you can't really have them colliding with each other if they're not moving, right? So we're going to see that liquids and gases are going to be kind of our area where we're going to have reactions happening. Solids can react with gas or liquid, at the surface of the solid. So solids don't really react with each other, but you can have a gas react with a solid or a liquid react with a solid, because you have at least one of those components moving around, right? So you want something to be moving if you're going to be reacting with a solid. I'll just put that as well. Solids typically don't react with other solids. Just because, again, things aren't really moving around. You need something moving in there. And so we're going to see that as a result, if you have a solid in there, going back to this part, if you have a high surface area, you're going to have a higher rate of reaction. If you're reacting at the surface of a solid, so the more surface you have, the more likely you're going to have your gas or liquid come in and bonk it, or do whatever it needs to happen at that solid interface, and that's going to increase your rate of reaction there. All right. So your state of matter will have an impact. If you're a liquid or a gas, you're going to be reacting quickly. If a solid is a component of your reaction, the surface area of that solid will be important. So that's why a lot of kind of research is going into making those quantum dots. We talked about those last semester, or just nanoparticles. If they're spherical, the smaller your sphere is, the larger surface area to volume ratio you have. So the smaller you can make your spheres, the larger your surface area. The more surface area you have, the faster you can react your things. So, for example, in your cars, you have a catalytic converter in there. That is a field of just surface material with large surface area that you're going to be reacting nitrogen oxides and sulfur oxides with, or carbon monoxide, to kind of fully convert those into less harmful products. Not to say that those gases that are produced are not harmful, but you're transforming them into less harmful ones by using high surface area catalytic converter. It's one of the most expensive pieces of your car, believe it or not, just because the metals that are used as these catalysts are going to be kind of ones that are not very common, like iridium, for example. Pretty rare metal. Comes from space, actually. We don't have too much of it on Earth. We get it from meteorites. Exciting. Anyways, where were we? That was number 3. Okay, so here's number 4 then. Speaking of which, the last thing you can do if you wanted to mess with your rate of reaction is throw a catalyst in there. This is going to change your reaction mechanism to make things easier, or just more likely to react. Mostly this happens by aiding the kind of just, what's the word I'm looking for, position and orientation of molecules. So we're going to see that catalysts do that. One important thing to note is that catalysts do not get used up. They don't get used up in a reaction. So you only need a small amount of a catalyst to help your reaction out. This is, in fact, perhaps the reason... Actually, it's not even perhaps. It's definitely the reason that life exists is because of these catalysts. So, by and large, the things that do things in our bodies are proteins. Proteins carry out all the, functions of the cells that we need to happen. And, keeping ourselves at 37 degrees Celsius is relatively low, comfortably speaking, where reactions aren't necessarily happening by themselves very quickly, But we have, millions of proteins in our bodies that are catalyzing reactions, that are making things happen much, much more quickly than they would be happening otherwise, without having to raise our temperature. Because if we were, if we had a body temperature of 100 degrees, of course the reactions would be happening faster overall. But maybe, we don't want these reactions to happen very frequently. We want to have some, means of control over reactions that are happening in our bodies. And so, that's why, life on Earth is pretty much all roughly around 37 for terrestrial things, thereabouts. And we're going to see we have very, kind of similar enzymes to other species. They always say, we have like 90% of our DNA in common with a banana or whatever. I don't know these percentages, but a lot of the enzymes that we need are going to be the same enzymes that other living creatures need, because they all need to convert, glucose into energy and blah, blah, blah. So, yeah. Where was I? Oh, yes, catalysts. So those are kind of the four ways we can mess with our reactions. And so, messing with these will give us a bit more control over how a reaction is happening. Especially if you go into organic chemistry, you're going to have thermodynamic products. We're going to talk about thermodynamics later on in the semester, versus kinetic products. And you can kind of force a reaction to choose one product over another based on these four things here. Anyways, that's kind of how we can mess with reactions. Let's just take a moment to look at how reactions happen. Perhaps we have, hydrogen and chlorine coming together. The hydrogen's going that way, chlorine's going that way. They bonk into each other, and now we have two HCl molecules. Hooray, we did it. What's important to note is that the light blue, perhaps, these molecules, they need to have enough energy to break their bonds. Remember that bond breaking is always endothermic. You have to put in energy to break bonds. However, we've learned that when you form bonds, you release energy, right? However, in order for those original bonds to break, they have to have enough energy when they collide. So we have our HH bond here. I'm just throwing out, some random things here. So in order to break that HH bond and that Cl-Cl bond, in order to form the HCl bond, in order to do that, the molecules need enough energy for that to happen. So they need to be able to break their own bonds in order to then form the new one. So if they don't have enough energy, whether that's a factor of temperature or whatever, they're not going to be able to react. So having enough energy is going to be an important thing for how reactions are happening. So if something is cold enough, if there's not enough energy to break the bonds, the reaction is not going to happen. That's why, for example, if you just have gasoline sitting out with oxygen, the molecules are not hitting each other fast enough quite yet in order for a reaction to take place between them. In fact, that one you're going to use something called activation energy to be overcome there, and then that's going to be kind of like the spark that gets things going. So as soon as some have enough energy, then you're going to be releasing other energy, and then that can go to chain reaction and have all that sort of fun explosion stuff happening. Anyways, we're also going to see that perhaps our molecules come towards each other in a different way. Maybe they hit each other this way instead. And this turns out not to work, even if they have enough energy. So we're going to see that the orientation of the molecules is also important. They can have as much energy as they want, but if they're not oriented the correct way, they're not going to react with each other. So they have to collide both with enough energy and in the right alignment or orientation for the reaction to happen. So maybe there's no possible way to form an HCl bond if they were to collide this way. These are just kind of, fake little examples here, but the point is the same, right? So you need two things for a reaction to happen. You need enough energy to break your own break bonds so you can form new ones, and then you also need your collision to happen in the correct orientation. And so that's the kind of the big things that these four kind of topics or things that we saw before are going to help out here. So your temperature is going to really affect the collisions here, that they're going to collide with enough energy. The more concentration you have, just the more likely things are to hit each other. And then with the catalyst or the surface area, again, the surface area and the state of matter also deal with being able to collide. You have to be able to collide, of course, in general. And then the catalyst here is going to be helping to orient your molecules. So the catalyst will be helping out that last portion a little bit. Often they'll just kind of bring things together in exactly the right orientation, and things will be able to, magically happen, and poof, now we have our molecule of interest going on. Cool. All right. So let's go back to some rate stuff now. Back to rates. So let's look at some fake reactions here. We have two things we can look at with a reaction in general. We can have the average rate or the instantaneous rate. We have kind of two things we can look at. And so here's an example of a reaction happening. This is going to be concentration. I'm sorry, this is time. I'm lying to you. This is concentration over here. And let's say, we have here, we'll even go up to the top. 1, 2, 3, 4, 5, 6, 7, 8 minutes. I don't know. And let's say we have there we go. I've labeled my graph. I'm such a beautiful artist. Try not to be jealous of my artistry here. But here's a potential reaction. Looking at these, we can go ahead and evaluate two different things here. We can look at the instantaneous rate as well as the average rate. Look at the average rate first. That's going to be just like we looked at before, the change in concentration over time, where that is going to be your final concentration minus your initial concentration over time. I guess change in time, so it should be your time final versus your time initial. Yeah, we can throw a delta in there also. Change in time. If we look at this, let's say apparently our reaction has stopped at 0.25 molar. Our initial concentration was 1 molar. And in fact, let's just make the sig figs nice and easy for us. versus the time, we had 8 minutes minus 0 minutes. So this reaction becomes negative 0.75 molar per 8 minutes. And if we were to do the math there, simple math, hopefully Kevin has done it for us. I mean, I can divide 75 by 8, I hope. We do that, we get, let's say, 9.4 times 10 to the negative 2 molar per minute. Hooray! That is our average rate. So we're looking at, the initial and final conditions for both the concentration and the time there. So that's going to be our average rate. However, we can look at the rate at, just a little section instead. Let's look at just this section here, the purple section. We can do that as well and find the instantaneous rate. That's going to be technically the tangent slope at that point, but let's not worry about that. Well, we can just go ahead and do the same idea here. So instead of having the initial and final concentrations or times, our instantaneous rate is just, we're looking at 2 particular concentration points and 2 particular time points. Notice this is just a slope formula. Again, if you have your graph, it's just the slope of that. So if we're looking at that, we had 1 minute, and apparently this is 0.75 molar. We can look at that. If we do so, our final concentration was... Oh, by the way, I just got rid of the negative sign for the other one. Remember, we just talk about things as positive, so I just threw out the negative. We don't care about the negative. This is going to be, what was it, 0.75 and 1. Okay. Our time 2 was 1 minute minus 0 minutes, which is going to be 0.25 molar per minute. So we're going pretty quick, relatively speaking. This is an order of magnitude higher than our average rate. We could look at another instantaneous rate. Let's look at maybe one down here. Let's look at the difference from 0.5 to 0.25. I don't know. It's kind of a really big area to do an instantaneous rate, but we'll do it anyway. Oh no. I don't need you to translate my horrible writing. All right, what do we have here? So we have 0.25 and 0.5. Let's just go ahead and look at this other rate. And what were those times? 0.25 is at 7 minutes, and 0.5 is at 2 minutes. I guess I'm being a little bit blasé with our sig figs here, but I'm allowed to do that. Doing this, it's what, 0.05? Is that correct? 0.25 divided by 5. Please tell me that's right. It is. Hooray. Here's a 0 there. Why not? What do we notice about these? Let's look at all 3 of these numbers, actually. What do we notice? Of course, they're all different, right? We see that this is relatively fast. However, if you look at later on in the reaction, we have a relatively slow rate happening. And our average rate is, in this case, it's somewhere in between them. So all these can be totally different. What's important to note here is that reactions slow down over time. The reason for that is because the concentration is depleted, right? If having more concentration makes our rate go up, having less concentration, exactly, less concentration means we're going to react slower. Just because, again, we have fewer things that can collide, so probability speaking, they're not going to collide as often. Our average rate, though, just describes the overall process. So, your average, I think the common analogy here is that, if it takes 2 hours and 15 minutes for me to drive to LA and it's, I don't know, 161 miles or whatever, I can figure out my average rate for that particular trip. Which would be just 161 divided by 2.25. There's my average rate. However, at any given time, maybe I'm going 10 miles per hour because I'm driving in the residential area trying to get to one of the big streets, and then maybe I'm on the 14 and I'm driving 70. It's just 70 because that's the speed limit, right? But you can see my instantaneous kind of speed at any given time could be whatever it is. But my average rate will just be kind of one whole number. So if I were to just look at my speedometer at any given time, that's my instantaneous rate. However, my average rate is just determined by my starting and ending conditions. So whatever those happen to be. Cool. Any questions on that sort of thing? So your instantaneous rate, just, you're looking at a fragment of the whole thing. Your average rate, you're looking at the entire thing. That's the difference there. And then, of course, reactions are slowing down over time. That's another thing we've got. All right. In that case, let's talk about more stuff. So, if we want to look at how we can relate rates to chemical equations, how do I spell equations? Let's see. There we go. We can do that. We're going to see that for a given reaction, where these lowercase ones are our coefficients, these little letters, whatever these components happen to be, we're going to see that the rate of the reaction is going to be equal to the change in A over time. Let me just make this a little easier. Where we actually are going to be using the inverse of the coefficient there. So if your coefficient is 2, you're going to end up with a rate that is half your concentration change over time. This would also be the same rate as the concentration change of B over time, or the same as concentration change C over time, or the same as 1 over D times concentration of D over time. Notice here we've put those negatives in. Those negatives there are just to make things positive. Don't really worry about it. But we know that these are negative because the concentration of reactants decreases, while the concentration of products increases, right? So exciting. So we know that the A and B in this reaction are reactants. Those are being used up, so their concentration is going down. We are forming D and C and D, so those ones will be going up over time. So that's why those are just written as positive. Again, here, I don't really care. Just make everything positive. The end. Easy. Just making things a little bit easier for ourselves. Just so we can think about things as, you know, a rate being a positive component. Alrighty, so if we look at an example here, notice that all of these would be equal to each other. So the rate at which A is decreasing would be equal to the rate at which C is being produced, depending on their coefficients. Let's look at an example. Ozone being depleted, turning into oxygen here. Both gases, so thankfully things are going to be working out nicely here. And let's say the rate of oxygen being formed is 6 times 10 to the negative 5th molar per second. This is an instantaneous rate. Let's see if we can figure out what the rate of ozone depletion is based on this particular thing. So we know that we have negative half the concentration of ozone over time is going to be equal to 1/3 the concentration of oxygen over time. Right? Just from the same thing from before, we just have 1 over the coefficient times our concentration change. Thankfully, because this is happening at the same time, we can just get rid of the time component. Actually, we probably shouldn't. But, yeah, fine, we'll keep the time component. Bleh. However, we do know that we have a value for our oxygen. So we know that the ozone concentration change over time is going to be 1/3 times this value that we have here. Right? That is the oxygen over time concentration. So we know that the change in ozone over time is going to be 2/3 times 6 times 10 to the negative 5 meters, not meters per second, molar per second, which is going to be equal to 4. I'm sorry, I should not be writing calculator speak. Molar per second there. So in this case, it's going to be negative because we're decreasing it. I'm going to get rid of the negative because we don't want to think about that. Exactly. So it's just going to be 4. So that's how you can relate these things to each other. So we're going to see that when we talk about more complex reactions, that this sort of thing will be very helpful for us. Alrighty. Cool. Any questions on this stuff so far? Hopefully nothing's too crazy here. Okay. Let's do another one. So, we have a word problem here. This one is from your book. Actually, both of these are from your book. But substance A is disappearing at a rate of, let's see, 4 molar per second, 0.04, I guess. B is appearing at a rate of 2 And C is appearing at a rate of 6 molar per second. I guess I'm in the habit here. Capital E, I mean times 10 to the. So 6 times 10 to the negative 2, 2 times negative 2, 4 times 10 to the negative 2, that sort of thing. So let's try and figure out what's the equation. So how are we going to approach this? Well, we know that, just looking at some of these things, we have one that's disappearing and one that is, I don't know how to speak. One is disappearing, two are appearing. Yeah, so we're definitely having some sort of thing happening here, right? We're having compound A decomposing into products B and C. That's kind of our bare bones here. However, we know that we have some coefficients here, perhaps, that we need to deal with. So in order to have the equation, we would need our coefficients in order to balance it, right? So we know that, for example, 1 over A times 4 would be 1 over B. I'm just getting rid of the negatives. Technically, this is a negative and that's a negative, but now they're both positive, so hooray. So looking at these, what do we see here? What information does this give us about the coefficients here? Well, if you solve this equation, if you get B over A is equal to 2 over 4, well, that's the same as saying 1/2, right? So that's saying that if B is 1, A is 2. I have the opposite, Kevin. Multiply both sides by B, divide both sides by 4. So you should get the opposite of that. Right? Double check. So this tells us that relative to A and B, their coefficients are 2 and 1. But let's go ahead and check the relationship of A to C now. If we look at those two, we see that 1 over A times 4 saves 1 over C times 6. Just kind of omitting our units here. We have C over A equals 6 over 4. Which is a 3 to 2 relationship. So that tells us C equals 3 when A equals 2. And so, scrolling back up here, we're able to see that our coefficient of C should be 3. So whatever this reaction happens to be, we have 2 molecules of A turning into 1 molecule of B and 3 molecules of C. Or formula units or whatever things are happening here. Does that make sense? So we're just relating their rates to each other in order to figure out our chemical equation. So this would be, again, an experimental method for us to kind of figure out something chemically speaking, like sort of about the mechanism of this reaction. We'll have more insight later on, but for right now, just kind of this is bare bones. Kevin, did you double check that? Did that work out? Okay, cool. Yeah, so that those would end up being your coefficients here. We can do the same thing looking at numbers instead. So here's a reaction. What is it? 4NO2 plus oxygen. All right, and it's found that the rate of N2O5 decomposition, the rate thereof, is 4.2 times 10 to the negative 7 molar per second. We can figure out the rates of nitrogen dioxide and oxygen. I really should not be writing in shorthand. Oh well. And then what's the rate of NO2 being formed? 2 questions here. But we're going to be doing exactly the same thing. So, reaction coefficient of dinitrogen pentoxide is 2. So we're going to have 1/2 times this 4.2 times 10 to the negative 7 molar per second is equal to 1/4 times the concentration of NO2 over time, which would be the rate of NO2 formation. So doing this, I can maybe do this in my head. Maybe. Should just be twice as big, I hope. 4, yeah, multiply by 4. Yeah, that's all we got to do. Okay, so that's going to be 8.4 times 10 to the negative 7 molar per second. I don't know why I'm putting parentheses. Don't need that. We have our answer. So we're going to see the rate should be twice as big because we're producing twice as much, right? We can do this if we really wanted. We could go ahead and do stoichiometry on this. We could just do plain old unit conversion, but I think this is a little bit faster. Just looking at the rates, we're producing 2 molecules of NO2 for every molecule of N2O5, so we should be coming up with concentration twice as fast as we are depleting the reactant. If we do the oxygen one, we can go ahead and do that. It's 1/1. And so therefore the oxygen concentration change, I'm just getting bigger and bigger with my writing, aren't I? Would be 2.1 meters per molar per second, not meters per second. Doing too much unit, or we're doing like basic unit conversion in 101 today, so I'm all about meters per second right now. So there we have it. Awesome. Any questions on that one? Alrighty. In that case, we can kind of start talking about rate laws then. Where, when we have components happening within a reaction, we can frame them in terms of either the products or reactants. Usually we talk about it in terms of reactants. But we can go ahead and describe the rate of a reaction being proportional to the concentrations of the reactants, however many reactants we have there. And we're going to see that the concentrations will have some effect based on their function in the reaction. No, I don't like the word function. Stuff about the physics. There we go. Where M and M are often they're often positive integers, but they could be negative or zero. Not very common, but they could be. We're going to see that the rate of a reaction for whatever A plus B turns into who cares. The rate of that reaction would be proportional to the concentrations. And we often describe this as having some sort of proportionality constant. Relating to those two reactant concentrations. This is called the rate constant. And it is indeed a constant if you are at constant temperature. So this is a temperature-dependent constant. So we're going to see that a lot of the kind of examples we're going to be doing, we're going to, of course, have constant temperature because we don't want to be messing with our rate constant. And we're later going to be able to use the rate constant to be able to predict the amount of product we have at a particular time in our reaction once we integrate these things. But for right now, we just have kind of the basic rate law here. And so this rate law, we're going to be able to actually determine experimentally the only way to figure out a rate law is to do experiments. And of course, this is something we would normally do in the lab. But of course, COVID has just ruined everything. Hopefully we'll be able to get vaccinated soon, but that's a whole nother matter. So we can't just, say, M and N are just our coefficients, though sometimes they will be your coefficients for the reaction. You have to do this experimentally. And so how that might look, do we have time for this? I don't think we do. So I think tomorrow we'll start with how to determine the rate law for a reaction. And we'll go over working with that. So, any questions on kind of the stuff we've done today, this kind of intro to kinetics that we started talking about? Let's see. I guess you guys do have other homework you're working on anyway, so keep on chugging on that. I think there are 2 simulations due this weekend. One's on safety, one's on solution preparation. And then the other thing you have is you've got homework that's due. So that's due Sunday. I'll probably come up with the key for that Monday or Tuesday. So try and make sure you submit it on time for maximum points. I don't really have any other announcements. We're just going to keep chugging on as usual. We're going to be working with this rate loss stuff tomorrow. We'll continue on. We'll have our data table. That's kind of what we need to use to figure out our rate law. So we'll have all this data to work with. It's going to give me the time to write that all out. So that'll be good. All right. So we'll just end 5 minutes early, I guess. Happy Tuesday. And yeah, I guess I'll see you tomorrow. If you have questions, throw them in Discord or, bring them tomorrow. Happy to go over them. Or if there's anything now, we can go over it. But hopefully this stuff is not too crazy so far. It will get there, don't worry. But not quite yet. Alrighty, well, see you later.